Hello, Professor. Thank you very much for taking time to review my application. My name is Rui Zhang. Now I'm a postdoctoral fellow in the Department of Material Science and Engineering at UIUC. In this presentation, I will first introduce my education and research background, then move to a summary of my research contributions in soft matter theory and computation. Finally, I will summarize my future research plans. I received a Bachelor of Science degree in 2003 from Tsinghua University, where I systematically studied fundamental math and theoretical physics courses. I then joined Professor An Changshi's group at Mathematics University to study polymer physics. I received the Master of Science degree in 2006. My thesis presents theoretical studies about the PFS polymers. I received a PhD in material science at UIUC in 2011. In research advised by Professor Ken Schweizer, I developed the first microscopic theory for coupled translational rotational glass dynamics. Due to this pioneering work, I received the Redshift Award for Outstanding Graduate Research from the department. I have had 2 postdoctoral appointments. Prior to the current position at UIUC focusing on glassy dynamics in mixture systems, I spent 2 years in Professor Monica Overa de la Cruz group at Northwestern University, working on computer simulations of non-equilibrium colloidal self-assembly. So my research has revolved around glass dynamics and self-assembly in different soft matter systems. Below, I would like to summarize my representative works in these 2 categories and their impact. The amorphous glassy states can be achieved in diverse soft materials, such as organic molecules, colloids, and polymers. In these states, the elementary units are transiently localized, and occasionally they will hop to a new champion position, driven by thermal fluctuation. This large amplitude real event is called activated hopping, which is a fundamental process governing the glass material's relaxation, transport, viscoelastic, and rheological properties. My research is built on the nonlinear equation approach developed in Schweizer group, which is the first microscopic force-level theory capable of treating activated hopping. Prior to my work, the formulations were only constructed for simple one-component sphere system. Glass-forming materials in real world often presents additional complexity. Complexity 1, many interesting properties of long-cycle glass formers stem from their unique translational rotational coupling. Complexity 2, for multi-component systems, there exists unique inter-component coupling, and I have made major theoretical contributions to these 2 important topics. My PhD research addresses the first topic, coupled translational rotational glass dynamics. The size-level force time coverage functions form the basis of the theory. Applying mode coupling and factorization approximations, a closed form of this function can be derived, where the structure inputs are computed with integral equation theory. The key idea is to introduce 2 dynamic order parameters defined as a particle's translational and rotational displacements relative to its initial position. The final form of this theory appears as 2 coupled nonlinear equations. The central theoretical object is called a dynamic free energy surface, whose gradient relative to the 2 order parameters quantifies the confining force and torque on a tangled particle due to its surroundings. Shown here is one example of the dynamic free energy surface that exhibits a 2-step activated hopping process, where the rotational hopping barrier is much lower than the translational hopping barrier. I have applied the theory to study diverse dynamical properties for glass-forming long-cycle colloids. Shown here are some representative results. I have made the first systematic predictions about kinetic array phase diagrams for a type of colloids called dumbbell-shaped colloids. On the left is one example of the phase diagram for a specific aspect ratio, 1.3. This system has been fabricated and studied by Chip Rogowski experimental group. Here, x-axis represents volume fraction and y-axis represents interparticle attraction stress. I predicted a rich set of kinetic array phases corresponding to quantitatively different features exhibited in the dynamic free energy surface. The complex interplay between caging and bonding constraints and the interplay between translational and rotational motion generates this richness. and my prediction has been well tested by experiments. My theory also quantitatively captures some unusual mechanical and rheological properties observed in experiments for non-static colloids. The right figure shows the dimensionless yield stress for dense hard dicolloids with 3 different aspect ratios. The theory quantitatively reproduces unusual double yielding behavior observed in experiments for weakening anisotropic hard dicolloids. My PhD research has provided insight to a broad range of soft matter science issues. Shown in this yellow box are some examples. My current research addresses the second type of glass material complexity for mixture systems. Consider a binary mixture, let's call the relatively faster component penetrance and a slower component matrix. Quantitatively and universally addressing how matrix facilitates the penetrance hopping poses the most challenging theoretic task. In fact, this was a long-lasting unsolved problem in Schreiber group. I have developed an innovative approach called self-consistent cooperative hopping theory that has fully solved the problem. The key idea is to introduce a new so-called coupled dynamic free energy function concept. A quantity called dynamic coupling parameter plays a central role to derive the formulations. This parameter is defined as a ratio between the penetrance hopping jump distance and the matrix cooperative displacement to facilitate this hop. So this parameter serves as a measure of the penetrance matrix dynamic coupling. A temporal coincident self-consistence condition is employed to find the physically unique value of this parameter. Okay, this slide summarizes the application of this theory to glassy polymer molecule mixtures based on a physically justified cost-screening scheme that maps the system to a model sphere mixture. Shown here are 2 case studies. In both figures, curves represent theory results and symbols indicate experimental data. The right figure addresses temperature dependence of oxygen diffusivity in 4 different polymers. By adjusting only one parameter, the penetrant matrix diameter ratio, a nearly perfect match to experimental data can be achieved. As a comparison, the phenomenological free volume theory often requires more finite parameters to achieve this level of accuracy. Moreover, my theory is a far more general approach to address diverse dynamical properties for glassy mixtures. The left figure considers an example for large organic penetrants. Unlike gas molecules, their loading in polymers can be high enough to generate significant plasticization or anti-plasticization behavior, depending on specific material chemistry. In the toluene polystyrene example considered here, both the toluene diffusivity shown in the main panel and the polystyrene glass transition temperature shown in the insects exhibits a clear plasticization behavior, and the theory quantitatively captures their composition dependence. My theory can be used to address diverse practical polymer materials issues. 3 examples that I'm currently investigating are listed in this yellow box. So now let me turn to the second category of soft matter problems that I have been working on, self-assembly. We can broadly classify self-assembly structure into 3 classes. The first is equilibrium assemblies. In this case, the system has thoroughly explored the energy landscape, and the structure corresponding to global energy minimum will be dominant. The second class is called kinetically trapped assemblies. In this case, some structures located at local energy minimum are prevalent in the system. They can be trapped into this metastable state for a long time. Kinetically trapped assemblies are dependent on specific dynamical pathways, so kinetics must be considered in order to gain a full understanding. The third class is called energy-driven far-from equilibrium assemblies, sometimes also called dissipative structures. This type of assemblies must be unnecessarily maintained by continuous energy injection, while living organisms are experts creating and utilizing such structures. In synthetic world, we are still in a very primitive stage. General theory remains elusive, and simulation is a very valuable tool. Below, I would like to summarize my key results related to each class of self-assembly. So I have recently completed a general free energy model for self-assembled micelles formed by crystalline coil diblock copolymers. As we know, amphiphenic diblock copolymers in selective solvents will form micelles with saurophobic blocks in the core and saurophilic blocks in the corona. An emerging scheme is using crystalline polymers to serve as the core blocks. Unlike traditional coil-coil diblock copolymers, several intriguing no-dimensional self-assembly structures have been observed, such as rod-like and tube-like micelles. Mitch Winnick and Yermanis experimental groups have done several pioneering works using PFS based on copolymers. So currently, the theoretical research is still far behind experiments, and the significance of my model is that it addresses all four micelle morphologies observed to date in a unified manner. In previous work on Nermana structures, Professor Stephen Chen had pointed out that multiple competing energetic factors could lead to Nermana structures being thermodynamically determined. So this represents equilibrium structures. My model assumes this thermodynamic control principle works for all four micelle structures. The fact that my calculations will capture experimental trends will support this assumption. Shown here is an example of morphology phase diagram. Y-axis represents polymerization index for Crowd blocks, and x-axis represents a chi-parameter between Crowd blocks and solvents. A very interesting thermally reversible rod-tube transition observed by Winnick-Manus team can be well explained by my model as a chi-parameter controlled morphology transition. As an additional merit, my model can predict some detailed micelle characteristics beyond current experimental resolution. Some examples are summarized in this yellow box. The second and third class of self-assembly systems are in the non-equilibrium regime, so it is important to have some tool can quantitatively track their detailed kinetics. At Northwestern University, I have learned and extended allowable kinetic monoclonal simulation approach, and based on this tool, studied several interesting non-equilibrium colloidal phenomena. Advantages of this method include the transition probability being rigorously derived from dynamical equations for Brownian objects and good numeric stability and computation efficiency. Shown here is a summary of my study of kinetically trapped ionic assemblies of oppositely charged colloids. For a wide range of solution conditions, previous studies have established the fact that certain chloride type superlattice is the equilibrium structure. My simulation work pointed out for the first time that these conditions could, however, generate distinctive kinetically trapped ionic assemblies, even starting from the same initial condition. In other words, between the same and the final configuration, a rich set of long-lived, non-equilibrium ionic assembly structures can be harvested. Based on my knowledge, the kinetically trapped self-assembly scheme is an emerging strategy used in the area of supramolecular polymerization. In this regard, my work represents a good proof of concept in the colloidal context. I also made several original contributions to one emerging soft matter topic, colloidal self-replication. In an ideal realization, the self-replication is driven by periodic past energy inputs. When energy is injected to the system, monomeric units spontaneously assemble with templates and are copied into new templates. When energy is off, different units disassemble and disperse with Weyer's diffusion. I first considered a hypothetical scheme inspired by less switchable nanoparticles in collaboration with Borisky's experimental group. I developed the first quantitative evidence that self-replication can be optimized by controlling the frequency at which energy is supplied to the system. This novel work about the optimization of self-replication was featured as a cover story in Agrochem. Later on, I turned to a design problem. I devised an explicit scheme based on patch colloids and demonstrated that they can display accurate exponential self-replication. One self-replication event captured by my simulation is shown here. In the final part, I would like to discuss my specific future research plans. I sincerely hope I can join the institute to investigate this fascinating subject matter problems as an independent researcher. So shown in this red box at bottom outlines the central scheme of my research. I will strive to derive coarse-grained models that are reasonably informed by atomistic level information and integrate statistical mechanical theories and computer simulations into sufficient combinatorial tools that allow predictive and accurate calculations of different macroscopic properties, especially dynamical properties. The short-term derivative projects include to applying my mixture theory to study mixed glass gel behavior in biophysical colloids and structural dynamics relationship in three generic polymer molecule systems. I'm also interested in exploring the possibility to extend my model in crystalline coil copolymer system to study kinetics, motivated by the recent work about crystallization-driven image assembly from Winnick and Manners laboratories. Within the 5-year appointment, I'm going to systematically study the following 5 topics. The first topic addresses a cutting-edge area in responsive soft materials that marries colloidal anisotropy and field direct motion. I'm especially interested in exploring the following 2 ideas. First, recent experiments in charged Colorado system has observed an interesting switching between one crystal-like state and one glass-like state by using electric field. Based on this proof of concept study, I envision, and this cartoon shows, that external fields can be programmed to accelerate nucleation or trigger kinetic arrest on demand and realize multiple types of condensed phases, both ordered and amorphous, in a single system. Second, using non-spherical colloids, it is possible to realize fast phase switching by precisely directing local rotational motion. I will combine and extend my tools developed from previous glass dynamics and self-replication work for non-spherical colloids to explore the fundamental physics around these 2 ideas. Proposed strategies include to derive stochastic equations of motion, incorporating collective dynamic order parameters, and to generalize the kinetic Monte scheme to involve non-local modes. I'm hopeful this research will generate useful insights for colloid-based photonic applications. The second topic is activity ion transport in solid-state polymers, which is closely relevant to energy applications such as solid-state lithium-ion battery. While this topic has been studied by several groups using molecular dynamic simulations, the understanding is still very limited because of time-scale challenge. Simulations indeed find that ion motion in solid-state polymers often presents activity hopping characteristics, showing close resemblance to glass dynamics. Moreover, experimentalists have found that the correlation between ion diffusion and polymer segmental relaxation is highly non-trivial. Both strong coupling and strong decoupling behavior have been observed. My mixture theory, SCCHT, has shown great promise in addressing the activity hopping of penetrance and penetrance matrix correlation in a systematic manner. So it is a promising starting point to achieve fundamental understanding of the ion transport problem. In future, I will generalize this approach into a more powerful version to handle specific complexity associated with the ion polymer mixtures. First, one real-world complexity is that multiple penetrants coexist, such as cations, anions, and salts. The theory will thus be extended to a general n-component approach beyond the current two-component formulation. By introducing multiple dynamic coupling parameters, this extension is technically straightforward. Second, and a more challenging task, is to explicitly model the chain connectivity and the inter-segmental level chemical details. A tentative idea in my mind is to combine polymer integral equation theory and molecular dynamic simulation with the SC-CHT approach. The third topic centers around reaction diffusion process in self-healing polymer composites. I'm particularly interested in the capsule-based scheme developed by Professors Scott White, Nat Sutos, and Jeff Wu at UIUC. I have been in close communication with the experimental groups and gained a lot of useful insights. So for this system, the basic mechanism is that when damage occurs, the capsules are ruptured and stored healing agent will flow into the cracked plane to initiate a polymerization reaction that finally heals the damage. This is a cool idea, but because of the complex interplay between multiple polymers and functional molecules, this field is still heavily relies on trial and error. And my goal is to develop a robust quantitative framework to handle specific questions, including the both natural and triggered diffusion of agents molecules in different polymer regions, and elucidate the molecular level picture of a healing event driven by reaction diffusion process. I propose to develop a SC-CHT KMC integrated approach to achieve this goal. The basic framework will be an iterative loop in which the diffusion rate calculated by my mixture theory inform the transition probabilities of kinetic monocolor moves, and the KMC simulation will update the dynamic evolution of the whole system. Chemical reactions will be detected and realized by KMC simulation, similar as my previous self-replication work. So with that, I would like to express my gratitude to my three advisors, Professor Anchang Su, Professor Ken Schweizer, and Professor Monica Alvarado de la Cruz, for teaching me many wonderful things about soft matter and about life. I'm deeply appreciative to be given this interview opportunity and present my research results and future plans in front of all committee professors. Thank you very much.